Okay, so today Anika and I will be taking the third knowledge transfer session and we'll be covering decision trees, ensemble methods, and random forest. So we'll start with decision trees first. Okay, so firstly, obviously, what is a decision tree? And it's a supervised learning algorithm, which means that we are trying to predict known labels from certain features. And this can be utilized for both classification and regression tasks. So essentially, as the name suggests, it has a hierarchical structure where we have a root node, we have branches, internal nodes, and leaf nodes. So this is fine. This is about the structure of the tree. But what exactly is a decision tree? So it's essentially a bunch of nested if and else statements, and these conditions are evaluated at nodes of the tree. They're called decision nodes. So you make a statement, and the decision tree decides whether or not it is true or false, and you move on to the other decision nodes or a leaf node. So yeah, we can take an example to better understand this. So over here, this is something called the root node, and it's kind of opposite to what the name would suggest. A root starts from the bottom in a tree, but here the topmost node is called the root node, and you evaluate a condition over here, say age less than 30. So by convention, the left direction is true and right is false. And yeah, the intermediate decisions over here are called decision nodes, and these are called leaf nodes, and they give you the final outcome, whether that's a class or a continuous value. So yeah, in this case, it's a classification tree because you have discrete values and you have categories. And when you predict continuous values, you get a regression tree. So yeah, this is just the convention again. So yeah, this one at the top, like I mentioned, is called a root node. And all the branches after that, all the conditions which are evaluated at the other nodes are called decision nodes. And over here, you can kind of consider this to be a tree of its own, but since it's part of the larger tree, it's also called a subtree. And leaf nodes are the nodes where no other conditions branch out of it and you get a final outcome. Okay, so some more terminology that's associated with decision trees is the process of pruning, where after you make the decision tree, if you find that some decision node is not doing a good job of predicting on, say, a validation test set or a test set, you can choose to remove it or cut it down, and this can prevent overfitting and increase the robustness of the model. And a parent node is a node that is subdivided into more nodes, and these subdivisions can either be leaf nodes or more decision nodes. And yeah, again, they represent a decision or a condition, and a child node is what comes out of these parent nodes, and they represent potential outcomes or just the leaf nodes. And yeah, so let's look at how to build a decision tree now. So we'll be taking this example data set where we just want to predict whether someone likes Red Bull or not. And our three features over here are whether that person likes fruit juice, they like soda, and what their age is. So this is a classification tree. So obviously, because we want to build a decision tree, the first thing we have to do is decide what will be the condition at the root node. And we want to look at loves fruit juice and loves soda. At first, just for simplicity, we can just take the two discrete value features and predict using those whether someone would like Red Bull. And using this, we can have two of these trees. So the first one is loves fruit juice and the second one is loves soda. And over here, you get the proportion of people who love fruit juice but don't like Red Bull being 3 and the ones who do like being 1. Similarly for the other leaf nodes. And yeah, you can see over here, probably the first thing you guys would notice is there's just one leaf node over here that does the perfect job of predicting whether someone likes Red Bull or not. And that's because you have 0 people being classified into not liking soda and then liking Red Bull. And that seems intuitive as well. But the other ones are not giving us a definitive answer. So the ones that don't give us a definitive answer are called impure leaves, and the one that does is called a pure leaf. So you can see that over here. These three are impure, and this one over here is the only pure leaf node. Yeah, I'll just pause over here and ask if anyone has any doubts. Okay. Yeah, we'll continue. So just qualitatively, we can say that the second tree performs a better job of predicting whether someone likes Red Bull or not, but we want to be able to quantify this and measure just using numbers what defines how good a tree is performing. And we can do this using two metrics, the first one being Gini impurity and the second one being entropy and information gain. So because Gini impurity essentially gives the same results as entropy and information gain, but is just simpler to calculate because it doesn't involve logarithms, it's probably the more popular one, and we'll be using that to build our tree. So we'll just go over some convention. We're defining K as the number of class labels we have, and P is the probability of a data point belonging to a certain class label. So the Gini index is defined as the sum of squares of these probabilities, and Gini impurity is just 1 minus the Gini index. So since we only have two classes in our example, either yes or no, our Gini impurity just translates into 1 minus the probability of getting yes squared minus the probability of getting no squared. And this is done for both leaves arising from the node. And then to find the Gini impurity for the entire tree, we take a weighted average of the Gini impurity scores for each of the leaves. So let's start with the lost fruit juice tree. So we'll calculate the Gini impurity of the side to the right and the side to the left, and we'll take the weighted average of them for the entire tree. So yeah, the probability of yes for the right side is 2 by 3 and no is 1 by 3. So we do 1 minus 2 by 3 squared minus 1 by 3 squared to get this value. And similarly for the left tree, left node, we get this as the value. So now we take the weighted average based on how many data points are being classified into each of these leaf nodes, and we get 4 to the left and 3 to the right. And essentially, this just becomes 0.405 as the Gini impurity of this entire tree. Now we can do the same thing for the second tree, which is love soda, and we get this Gini impurity to be 0.214, which is a smaller value than the first one. So this quantifies how much better this tree is performing than the first one. So just to build some intuition of why this formula makes sense, we want to ask the question that makes the data as pure as possible or gives us as definitive of an answer as possible. So say I had everything, say the tree was performing a really good job and segregating all data points into one class, leaving the other probabilities as 0, then I would get Gini impurity equal to 0. And this is what we want, which is a perfectly pure leaf node. And if they're evenly distributed, this Gini impurity would depend on how many classes there are. But since we have two classes, we would just get 0.5 as the impurity. And this tells us that the leaf node is impure. And we could have done just 1 minus sigma pi. And there's a reason we do sigma pi squared. We get the square term because we are modeling a two-step random process. The first step being we are picking the probability of choosing a data point from any of these classes that we have, and also the probability of guessing that exact label for that data point. So we get pi squared over here. So now we've done it for columns that have discrete values. What about if we have a continuous value like age? So in this case, we take the average of adjacent rows and we use these to form our decision nodes. So yeah, we just take average of 7 and 12, 12 and 18, and so on. And we evaluate at the average values. So if we take the example of 9.5, age is less than 9.5 will go to the left and more than 9.5 will go to the right. So this is pure, although it is only classifying one data point, it is a pure leaf and we get the Gini impurity as 0. And this one is just a perfect split. So we get Gini impurity as 0.5 and we take the weighted average and we get 0.429 as a Gini impurity, which is, I think, bigger than both the values we got. So if we do the same process for all of the values, we get this as the Gini impurities. And overall, although this is the lowest Gini impurity we get for 15, it is still more than the Gini impurity we got for the love soda tree. So we pick love soda as our root. So we're just picking the condition that gives us the smallest value Gini impurity as our root node. And this process will propagate for every decision node, not just the root node. So yeah, we get one pure node over here and we get one impure node over here. So now since this is pure, we can stop worrying about this and move on to just the impure leaves so we can eventually make them pure. I'll pause if anyone has any doubts. You guys can hear me, right?
Yeah.
Yeah.
Okay. Yep. So now we just segregate the data into whatever data points and that ended up on this leaf node because these have already been classified and we don't need to worry about them. So yeah, all of these are love soda, yes. And now we have to split the left node based on whether they either love fruit juice or we can take one of the adjacent average values of these again. So yeah, these averages become these values. And when you do the calculation for Gini impurity all over again, you find that the 12.5 value will give you a perfect split with Gini impurity equal to 0. And we can compare this with the love's fruit juice again. And this does give you one pure leaf node, but this one is not pure. And so we get the total Gini impurity as 0.25, which is still more than 0 that we got for 12.5. So we choose age less than 12.5 to make the next split. And that is the end of the tree. So now we have segregated our data into all pure leaf nodes. And yeah, the tree has been constructed. So yeah, you can use it to predict if a person likes Red Bull or not now. And here we've used Gini impurity. We can look at the second metric now, which is entropy and information gain. So this is how the formula for entropy is defined. And this is sigma probability of a data point belonging to class I times the logarithm of that probability. And you can think of this as log of probability being a surprise factor and multiplied by the probability of getting that class. So you're trying to find the average surprise that you get when predicting a data point. So yeah, the higher the entropy, the harder it is to draw any conclusion. And entropy essentially means randomness even in other contexts, so it makes sense over here as well. And when we get entropy 0, that is when we know that we can end the process over there for that leaf node. And information gain is the expected reduction in entropy. So you calculate it by finding the entropy of your decision node, subtract the weighted average of entropy of the nodes that emerge out of it from it. So yeah, we again, like Gini impurity, we use this to decide which feature to split on at each step to build the tree. We can take a different data set for this one where we're just trying to predict the outcome as yes or no again, but this time based on colors being either red or yellow. So the entropy for just the decision node or root node would be probability of yes times logarithm of probability of yes, and similarly for no and the negative of that. And you get this value as 0.971. So which is pretty high value of entropy. And now we do it for each individual leaf node. So you see how many of these rows are have yellow as their color, and how many have red. And within those, how many of those map to yes and how many of them map to no. So this is the entropy you get for the rows that have color as yellow, and this is for red. And then you take the weighted average depending on how many of these rows are for each of the colors, and you get the entropy as 0.924. And when we subtract the weighted average from the entropy we got at the root, you get 0.047. And entropy gain will always be a positive value, but the more positive it is, the better for our split. So since this is a value very close to zero, the split is not favorable. And there will probably, in this case, there are no other features, but if there were more, there would most likely be other features would do a better job in segregating the data and reduce uncertainty. So just wanted to give like a brief introduction to regression trees. So it is very similar to classification trees in the sense that you're building the nodes in a similar way. And this is used to predict continuous numeric outcomes rather than discrete class labels like in classification trees. But instead of instead of assigning a class, you predict a numeric value. And the splitting is done in the same way, like we saw in that age feature. But the prediction ends up being the mean of all the values that end up at that node. The mean of the target values. And the impurity metric in this case can be something like RMSE or variance instead of Gini impurity and information gain and entropy. So yeah, this is just a visual example of a regression tree. So over here, you can see a bunch of data points, and these are conditions evaluated at the decision nodes. And you can see bounding boxes type of things that segregate the data and give you a value, one value for each of these boxes. So say x2 less than 0.3 would be this region. And then further, one more condition on top of that would be less than 0.8 would give you this box. And this would be the average of all these data points that lie within this box. Does anyone have any doubts? Okay. So we can move on to the code implementation now. Okay, so when we implement this in code, I've used Gini impurity to build the same tree as we saw in the first example. So this is that tree. And I've just mapped yes to 1 and no to 0 for all of these three. And we calculate the Gini impurity by seeing all the different classes within a feature. And we see the length of that class and how many of the values in that class map to that data point liking Red Bull or not. And we find the sum of square of probabilities of these and calculate the Gini impurity by taking the weighted average. Yeah, this function is just to find the left and right splits at a decision node. So we take less than as if less than as the right side and more than as the less than as the left side and more than as the right side. Okay, so over here to get the split at a node, we iterate over all the columns that we have, the features, and we find the Gini impurity over here. So for age, we calculate all the thresholds based on the averaging of adjacent values. And if not, we just take the half between 0 and 1 for the rest of the columns. And yeah, we just use the split over here. And yeah, we map all the values that belong to each left or right nodes. So now over here, we build the tree. So yeah, we get the split for the data, and this is a base case, and this is also a base case in case the tree is just empty. And that would just be directly classifying based on probabilities of something belonging to the Red Bull class or not. Sorry, Red Bull likes Red Bull or doesn't like Red Bull class. And we just call this recursively over and over, and it builds a nested dictionary type of structure where we get the left and right nodes for each decision node. And yeah, this is just a function to print what the tree looks like. So this is exactly the same as the example that we have done. Over here, I have broken ties using the soda column just because for reproducibility, but I don't think there were any ties. Yeah, so this is the tree that we get. We only get one value over here because one of them was a pure node.
Okay. So yeah, I'm going to be talking about ensemble methods. So yeah, ensemble methods in machine learning are just techniques which use multiple different models together. So you have multiple simple models and then you train them all separately. And then finally you combine their predictions to get an overall prediction for your task. So the point of this is training simple models like separately or like in certain ways in relation to each other is going to give you a more robust answer because you have different models having their say. So each model will have its strengths and weaknesses. And so combining all these is going to give you a robust answer and it's also going to prevent overfitting. So yeah, for example, if you are a music artist and you want to release your first album, you'd ask a bunch of different experts in like different genres and different instruments and etc. You won't just ask one person. So it's better to use different models with different strengths and combine their overall predictions to get your most for your best generalization. Okay. So yeah, why ensemble methods? Some particular reasons why these are good. So firstly, you get improved accuracy because if a certain model has a certain weakness and predicts certain examples wrong, that can be averaged out by another model, which because you're taking different says basically, like you're not relying on one model. So you'll get better accuracy. There'll obviously be more robustness to noise because if you're using a single model, it's more prone to overfit on certain noisy components. And yeah, you have robustness to noise and reduced overfitting. And finally, increased flexibility. So you have a bunch of simple models. It's easier to tweak the system to make it more useful to you. So yeah, exactly. So the point of using ensemble methods, the main point is to reduce overfitting. Uh, yeah. So if you can see, overfitting is like you take even outliers and you try to fit the model to those like wrong, noisy data points. So as you can see, it's the orange line. So to prevent this and to get like a good model which generalizes on new data, you need to take says from different models. So yeah, there's different kinds of ensemble methods. So there's bagging, there's boosting, there's stacking, and today we'll be focusing on bagging and boosting. Yeah, and before getting into that, first I talked about taking the overall prediction from different models. So how exactly do we do that? So this can be through voting, averaging, or weighted averaging. In case it's a classification task, you'll take voting. So the majority votes for the class. If there's like binary classification, if majority of the models vote for one class, that's going to be the final class. And if it's regression, you can use averaging or weighted averaging. So this totally depends on if the data set is continuous or not. So if it's a continuous data set, you'll be using continuous data sets, you'll use regression. So you'll use averaging or weighted averaging. And here, if the data set has models in which certain models are less accurate, less reliable, you use weighted averaging and give those models a smaller weight. So they'll have less say in the final prediction. So yeah, and in voting, there's two types. There's hard voting and soft voting. So hard voting just takes into account the final prediction of the model. So it predicts one, and like you don't really take its sureness into account. You just take the final prediction. So if multiple models have the same final prediction, you just or like majority of the models have the same final prediction, you take that as the overall one. Whereas in soft voting, you take in like the sureness. So if it's one model is, so you take the sureness of each model. So for class 1, ML model 1 has 70% sureness, and for class 2 it's 40%. Model 3 is 90%. So you take the average of those percentages. And for the zeroth class also, you take averages of the percentages. And so once you get the average percentages, finally you get the prediction. So this is how you do soft coding. And then, yeah, so let's get into the actual models. So bagging stands for bootstrap aggregation. So there's two steps here. So uh, so how you do this is the first step is bootstrapping. So what bootstrapping is it's basically taking randomized features from your data set. So you have a like set of data with like say 10 features. So what you do is to train the first model, you take a random set of features, like say 3 random features from those 10, and then you train it on that. And the next model in the ensemble method, you take different 3 random features. So basically, what this does is when you're taking random subsets of the original data set to train each model, it's getting trained on different data points essentially. So is when you take the combined prediction of all of these models together, it's definitely not going to be overfit because each one is trained on different data points essentially. So yeah, several number of subsets are taken from the data set with replacement, and they're assigned to different models. So the point this like with replacement thing is important. So when you take a data set subset out of the data and train it on the first model, you're gonna keep that data in the original set while you select for the second model as well. So this data that you chose for the first model, you can choose it again for the second model. It's not gonna just get like eliminated from the selection list. So the point is the same data can appear on each model and some may not appear at all in the entire process. So this is what creates more variations in the data sets you use to train each model. So this completely keeps you robust to overfitting. So yeah, and finally, after you train it on each subset of the data, you do aggregation. So the final outputs from each model, you aggregate it in some kind of technique. You can use voting or averaging or something. So random forest is just a type of bagging algorithm. Yeah, and the thing is, for random forest, the models that we use under some random models, they're decision trees. Yeah, that's what I said in the previous slide. Like some features are repeated because of random feature selection, some features are repeated. So for the first model, if you get 1 and 4, the second model also 4 is also appearing. So in all three, you get the fourth feature. But like you don't get 1 here and you don't get 2 here. So it'll be different and some might be repeated, some might not appear at all. So this ensures that there's no overfitting in the final predictions. Yeah, okay. So we've talked about bagging. So we just said we train. So the point of bagging is you just train each model on a different subset of the data. That's all you're doing. There's no other relation between the models or anything. So in case all the models just incorrectly predict the data, finally combining your predictions is not going to make it any better. It's going to be wrong. So what can we do to fix this? So here's where boosting comes in. So boosting is a lot more dynamic than bagging, where each subsequent model attempts to correct the errors of the previous model. So it's trained to focus on where the previous model was weak. So if the previous model makes a certain error in a certain data point, the next model is going to focus on that data point and to make it more correct, like make a better prediction. So this is going to be even better at predicting. So before we get into like specific boosting algorithms, are there any doubts? Okay, I'll continue. So the first one is AdaBoost or adaptive boosting. So I would say this is like one of the most simple boosting algorithms there is. So what you have is, I said that in an ensemble technique, you have different models. And in here, the models are just stumps, like they're not even complete decision trees. They're just very simple. They're just one branch of a decision tree, which is called a stump, one node and 2 leaves. So yeah. So in the first stump, you train on the training data and you get the classifications. And certain classifications is going to be certain data points are going to be classified wrong. So these misclassified data points, you're going to be giving it a higher weight, and you're going to be passing these weighted data points in the next model. The next stump or next model is going to focus on these incorrectly classified ones more than on the others. So like this diagram like says it better. So for example, this like red plus is classified wrong. So you're giving it higher weight, like you're increasing the size and for the next model, and that continues. So I like let's get into the actual math of like how this happens. So what you do is you start like while starting off for each data point, like 1, 2, 3, 4, 5, 6, 7, we have 7 separate data points here, and you have the outputs. And so first to start off, you just give them all the same weight. So it's just 1/7 equal weights. And then what you do is with these weights, you perform the first iteration. Then after you do the first classification, like you have to check how many ever you got incorrect. So in this example, you just got one example incorrect. So then you calculate a term called the total error. So total error is just gonna be the sum of the weights of the error rows. So the incorrect predictions, those weights. Here there was only one incorrect prediction, so it's just 1/7. So this is the total error. And so for this stump, you calculate something called performance of stump. So the formula for that is half of log 1 minus total error by total error. So this is gonna be less when your total error is high. So once you get this performance, like which is basically tells you how good it is at predicting, you use this to update the weights. So for incorrect data points, the updated weight is going to be the original sample weight into e power eta. And for correct data, it's going to be sample weight into e power minus eta. So basically, you're increasing the weight of this incorrect data points and you're decreasing the weight of this correct data. So how this error helps to how this weight helps to tell the next model to focus is like what you do is you get the updated weight. So here you just multiplied e power minus eta for all the correct ones and e power eta for the incorrect one. And you get the updated weights and you just normalize them. Then you have a cumulative class. So what you do is with this normalized weights, you basically create class intervals which are as big as this weight. Yeah, that's all. So for the second model, while you get the data set to create for like okay, sorry. For the next model, like after the subsequent model, to create the predictions, you're going to use a data set, right? So it's not going to be the exact data set that you used here. You're not just going to use all these data points. What you're going to do is you're going to generate a random number. So for this random number, if it falls in this interval, you're going to select data point number 1. And if the random number falls in this interval, like 0.172 to 0.672, you're going to select data point 3. So basically, this weight determines this range. So if the range is higher, it's more likely to get selected. So when it's a higher weight, because it was predicted wrongly, it's going to have a huge range. And it's more likely to appear in the new training data. You're going to select it multiple times in the new training data, while the other correctly classified ones are not going to be selected in the training data. They might be selected, but they'll be selected less than this one, essentially. So your next model is going to focus on this because it's going to have multiple instances of this one data point in its training data. So that's how each new model learns from the previous model in AdaBoost. So next, we'll move on to gradient boosting. So what gradient boosting does is the subsequent learners or decision trees are trained to predict the error values or the residuals of the previous predictions. So error value is essentially just the observed value minus the predicted value of this first model. So basically that error, it's going to predict the error, the next model. And so with each new tree, this error is going to keep decreasing, or this residue is going to keep decreasing. And it indicates that we're making smaller steps in the right direction. Okay, so the exact steps for this is you first, you have some training data. So you have gender, weight, and height here. And you have to predict age. So this is the final Y. Yeah, age is the final Y. And so you're gonna, so for first you make prediction 0. So for that, you just like take the mean of all these Y values. and initialize the predictions to the mean of the actual values. And then you create, you initialize it to the mean, and then you calculate residuals. So residual is just actual value minus prediction. So it's going to be age minus prediction. So 50 minus 39. So basically, this is how much you have to add to this prediction to get the actual value, like how wrong these predictions are. And so what you do is now you create the first decision tree. So like in this diagram, this is basically just one node. So this represents us initializing the values to that mean. And then you create the first decision tree. So the first decision tree is trained to predict the residuals from the features. So you have gender, weight, and height. So you feed these as X and the residual values as Y. So this decision tree is trained to predict these residuals. So then you update the predictions. You have like one initialized prediction. So the new prediction is going to be the old prediction plus learning rate into the predicted residual. So predicted error by the model, you're going to add to the old prediction. And now you get some new predictions, prediction one. Essentially, you're adding with this prediction 0, you're adding the residual predicted by the first model, and you get prediction 1. Then again, you calculate residuals with this prediction 1 and actual Y. Like prediction number 1, the new prediction, and Y is going to have a difference. It's not going to be perfectly correct again. And you get the new residuals. Then you keep doing this. Like the next model, the second decision tree is going to predict the residual errors made by the first model. So you're going to keep doing this until the residual value, like the error value, stops changing. It becomes minimal and stops changing. So you're essentially making small steps towards the exact age, and you'll get the like right prediction. Okay, so this is like it's a better visual of what I was saying. So you make the initial prediction as the average of the income, then you calculate the residuals, then you train a decision tree to predict these residuals. And one important point is, in case the decision trees have like multiple output values in the same leaf, you just average them out. And all these decisions, like averaging out the leaves with multiple outputs and initializing the prediction as the average of the income, why we do this is these decisions only make the minimize the loss. So like taking average of the income essentially minimizes the loss. That's the best value to take as an initialization. And yeah, so you average these and get the decision tree. Then these residuals that are predicted by the decision tree, you create the new prediction using those. Old prediction plus alpha into predicted residue. So like one question is like, why do we use a learning rate here? Because essentially we're predicting the residuals, right? We're predicting the errors. So if we add the exact residuals to the like original prediction, the exact thing where it is lacking, you're going to get the exact correct prediction. Why do you use a learning rate here? That's a question that I had. So why we use a learning rate is to prevent overfitting. So for example, if you look at this decision tree for example number 3. For this example, the residual in 1 second. Yeah, the residual income, like the actual income minus prediction is going to be -2. And the decision, like this is what we calculated using simple subtraction. And now the decision tree also predicts this to be -2. So if you exactly add this residual, basically prediction plus residual 3 minus 2, you're going to get the actual answer like with the first decision tree itself. So what this is it's like essentially just overfitting to this data point. You don't want to make huge steps towards the correct answer. You want to make small steps in the right direction so that you prevent overfitting. So that's why I use a learning rate. This makes it more robust. Okay, so finally, while calculating the prediction for a test data, what you do is you run the test data point through all of these decision trees that you created, and you add the prediction of each one. So you have the initial prediction, which was the mean, like 3 over here. Then you add the residual predicted by the first model. Then you add the residual predicted by the second model, and this residual is what is lacking from the first model and the original initialization. And this is going to be the further residual. So you completely add all of the predictions by each model to get the final answer, which is going to be the closest to the actual value. So that's how you do gradient boosting. And the final topic is XG boosting, or like extreme gradient boosting. So this is just an implementation of gradient boosting, and it has some specific things in it, some specific modifications that make it more efficient and scalable, and it's S3 more optimized. So what you do is here you use tree pruning and regularization. So tree pruning essentially removes branches from decision tree that are not as useful, and regularization like further prevents overfitting. So how you implement this tree pruning and regularization is like through these formulas. So we know that for normal decision trees, they are built based on mean squared error. Like you're minimizing, you choose branches that minimize the mean squared error. But here you don't use mean squared error, you use something called similarity score. So similarity score is the square of the sum of residuals. Like you sum up all these like predicted residual values and square that divided by number of residuals plus lambda. And here lambda is a regularization parameter. So what this does is, okay, one second. So if you have similarity score here, and for example, you want to calculate for this leaf, like the 0.5, 4.5 minus 1.51. You add all of these, you square them, divided by 3 plus lambda. So what lambda does is it reduces the similarity score to prevent overfitting. Basically the logic behind this is if you had like a leaf with just one prediction like -2, the decrease in similarity score due to lambda will be more than if you have more predictions. So if it's more unsure, you're essentially giving it a better like you're not decreasing the similarity score as much. If it has multiple things here, it's not perfectly sure that it's -2. You're like kind of rewarding it and saying, yeah, that's better, because if you have just one prediction, that's going to be overfitted. So this is better, and that's what lambda does. And you also have something called a pruning parameter. So to make this pruning parameter work, first you have to calculate something called gain. So I told you we have similarity scores for each leaf. So what you do is, like to calculate how well a branch, like this age is less than 40 branch works, you use gain. So it's going to be similarity score of this right leaf plus similarity score of the left leaf minus similarity score of the parent. So parent similarity score is just going to be like 1, 0, 0.5, 4.5, minus 1.5. All of these added together. Like imagine all of these in one leaf and calculate it for that leaf. So you get gain for this branch. And if only if this gain is greater than a specific pruning parameter, which is just decided beforehand, you keep this branch. Like if it's less than the pruning parameter, you just remove it completely. Age is less than 40 is a useless split. So you just stop that. So yeah, so pruning helps to remove useless branches, and yeah, regularization prevents overfitting. So that's the new things in XGBoost that are different from gradient boosting. And yeah, so like those are all the methods that we use for boosting. And finally, for evaluation of performance of these ensemble methods, you can use different things. So first thing is metrics, which we use for any model, like using precision, recall, F1 score, area under the receiver operating characteristic curve. Like these scores tell you how good a model is at generalization. And benchmarking, like for example, you just use one simple model, like for example just a single decision tree, and see how much better these other models are compared to that decision tree. So like if you're getting any payoff from doing ensemble. And also you have cross validation, which is just a special way of like testing generalization by using a data set that you have. Like instead of just doing one train test split, you kind of do multiple train test splits, and then you check the data on, like you check the model's performance on different test data. So yeah, this also tells you about generalization. So these are how you evaluate how good these ensemble methods are at generalizing and preventing overfitting. Okay, I'll just go to the code. It's like just a simple implementation of all these methods. So yeah, so like you can import all these ensemble methods from sklearn directly, and that's what I've done here. And then you're just generating like a synthetic data set. So with just like random numbers. So you have like your data, X data is going to be 200 samples and 5 features, and you're going to get random numbers between 0 and 1, and I'm just multiplying that by 10. And you're also generating like a synthetic class for each data set. So it's just going to be like 0 or 1. You're putting in like a Boolean value and converting that to int. So it's just going to be 0 or 1. And so this for classification, and also here's regression data. So this is also going to be 200 samples with 5 features. You're just multiplying a random constant with like each feature, and also adding some noise to get a linear, like not exactly linear, but like linear regression with noise. And you're just plain test splitting the data. Now comes building the actual models. So so you're just training a single decision tree as kind of like the benchmark model. So this also you can just get from sklearn. You don't have to do it from scratch. And then you build the random forest classifier. So here there are some special parameters that you need to add. So n estimators is basically the number of trees that you're using in the random forest. And yeah, maximum features just the maximum number of features that you take in each training step. And yeah, so you just fit the data and make predictions and calculate the accuracy. And then, yeah, also one special thing from sklearn and random forest is you can get feature importances. So basically, it will tell you how important a feature is and how good it is at predicting the data without overfitting. And yeah, and then we're just doing boosting. So like random forest was the only bagging method that we studied. And so now we have boosting. Here also it's a single decision tree regression tree. Like there it was a classification tree. And so you're building that. And then you have a gradient boosting regressor. So here again, n estimators is you're like putting a boundary on the number of trees. It's not gonna like keep going. And you're specifying the learning rate, which we discussed. And maximum depth is just the depth of each tree, like the number of layers in each tree. You're restricting that as well. Um, yeah, same. You're just like predicting the values for this gradient boosting algorithm. And the next one is add a boost. So add a boost also has a built-in method. And here for the model, you're specifying that it's a decision tree. It can be like any model, but you're specifying that it's a decision tree. And the number of estimators is 50. And this also has a learning rate. And yeah. And finally, we just visualized like one bagging method and one boosting method for like for 2 features to keep it simple and easy to visualize. So we're just selecting 2 columns from the X classification data set that we created, and train to split this visualization data. And then yeah, train the random forest on this. And that's the bagging method, and training add a boost on this. That's the boosting method that I chose. And yeah, this is just a function to plot the decision boundary for both these classifiers. And finally, if we look at the decision boundaries, you get the random forest decision boundary here and the add a boost decision boundary here. So yeah, I think like we'll come to an end.